Okay, hello everyone. We are here in the second year of the ESCOM webinars. Incredibly, but we started in December 2024 with our first webinar about weather because we are always interested in weather. And we're going to start our second year with another webinar about weather. So that is great. Hi, Ariami. How are you today?
I'm doing great, Camilo. It is snowy out there. How are you doing?
I'm fine. Today I'm in my coffee farm in Colombia. So here it's not snow at all. It's
Uh,
quite down there, but I think I have my own weather station in my home there in Little Dover, so I can check the weather. That is our today's topic. But unfortunately, I'm not there to know about snow because we cannot record snow with our weather station. But the good thing is that we have another citizen scientist in Little Dover, and they are collecting with cockroach the snow. That this was exactly the topic of our first webinar last year.
uh-huh. Yeah, absolutely. And we're actually here to talk about the weather monitoring, um, specifically with more specifically with Dr. Joel Finnis, climatologist from the Department of Geography at Memorial University in Newfoundland and Labrador. Um, Joel, would you like to introduce yourself?
Yeah, sure. So I'm a climatologist. I was trained in the atmospheric sciences. I ended up in a geography department, which kind of makes some sense for climatology. It originated in geography before being, let's call it, hijacked by physics when people got interested in modeling, et cetera, et cetera. These days, as people are trying to figure out how to use climatology to prepare for climate change, it's being pulled back into more interdisciplinary settings like geography. So it's kind of like coming home. But those interests in climate and extreme weather are still very much there.
For sure. Thanks for being willing to come out and give us this webinar. We wanted to have Joel come and present this webinar because all of us here at ESCOM, a lot of us have these weather stations that we have outside our home, either through Wonderground or through CocoRush. CocoRush for measuring rain and snow, Wonderground for measuring a lot of other climate parameters. But we were wondering, how can we use this weather data that we're collecting to help us learn more about the climate around us? We were also, one thing I do want to mention is that we were also hoping that if we have all this weather data, we can also make different representations of it. Things like artistic weather scarves, artistic weather blankets. We can't do that without knowing what this data means. So, Joel, would you like to start your webinar?
Yeah, sure. I think you can see my screen here. Yeah.
Yep.
Perfect. So yeah, I mean, I was invited to talk to you a little bit about your weather stations, their placement, and how to think about what's coming out of them. And of course, as a climatologist with weather interests, I always think about how to use them to understand the weather as it passes by, first of all. But then ultimately, I want to think a little bit more about what you can do with this data if you have a lot of time, or alternately a lot of measurements. Make sense of a broader climate picture, right? Building from what we see day to day in our backyards to an understanding of what we can expect and the range of potential weather outcomes that we might see. I do want to stress, though, that you are deploying a coastal network of weather stations, and in many ways, this connects right back to the origins of modern meteorology. The first time anybody ever tried to strategically deploy standardized weather stations, it was entirely focused on understanding coastal and marine risk. It was motivated by concern about safety on ships, safety for fishers, and making sure that people knew what was coming in advance so that they could make informed decisions. At the time, this was back in the 1850s, spearheaded by Vice Admiral Robert Fitzroy of the Royal Navy. They were thinking about pressure readings as an indicator of whether a weather system was moving through, specifically whether low pressures were passing by. And if they were, then you could expect that maybe some rough weather would come with it. So that's how we got to 1854. Vice Admiral Fitzroy was appointed the first meteorological statist to the Board of Trade. That's basically just saying he was our first weather statistician. And that office, which originally was just him and 3 employees, was really the precursor to the modern UK Met Office, the equivalent to our Meteorological Service of Canada under Environment Canada and, well, Environment and Climate Change Canada these days. So yeah, this is going right back to the origins of organized public meteorology. It was about reducing coastal and marine risk. By the time we get to 1855, they deployed a bunch of barometers at various different ports. They tried to put one in every single significant port in the UK. And this is what they look like. This is from the Orkneys in the UK. It's being dug into the concrete around the port. And it was just left there. Daily, people would go out and take measurements and try to interpret what was happening in terms of passing weather systems. This was an expensive piece of equipment. You couldn't put it in every single coastal town, but they looked for smaller, more affordable alternatives. And this was the solution they came up with initially. It was something they called a storm glass. You see the conditions inside that glass, the amount of crystals, et cetera, change in response to what the weather conditions are looking like. So if you do start to see crystals form, you can interpret that in many cases as a change in the combination of temperature and pressure. But that office also was responsible for the first things we would actually call weather forecasts, and Admiral Fitzroy himself coined that term. He was the first person to use the term weather forecast. So it's, again, all coming back to concerns around the coast and how to address them. Now, of course, these days, our network of weather stations and climate stations across the globe really is considerably more sophisticated. There's more measurements, more instruments out there. The backbone of this really are the stations that we've put in place to support aviation and defense. So this is an example of what we call an automated surface observation system. These are standardized. You will see them across North America with the same basic setup. It hasn't changed dramatically, even if the individual instruments might have been updated over the course of the last 10, 50, well, more than that, 30, 40 years really at this point. And we've got all these instruments listed. You can see that they're in a line. We've got precipitation observations, temperature and dew point sensors. We've got precipitation identifiers. We've got a wind observation from our anemometer that's collecting wind info at specified heights. We've got a ceilometer, which tells us how high up the clouds are. We've got freezing rain sensors as well, so we know when that freezing precipitation is coming through, and visibility sensors telling us whether we've got horizontal fog or blowing snow or something that will impede our visibility. And again, remember that these things are really laid out to support things like aviation initially. So we put them at every single airport. If you're going to run an airport of any substantial size, you have to have one of these things, and you have to be paying attention to what's coming in. We have the same setup in Canada. That one's from Texas, but just to give you a sense of what they look like in Canada, basically the same, maybe the arrangement's a little bit different, but the same basic instruments are all still present, and they're all still collecting those same standardized observations. These things at this point are automated, so they're just collecting data continually. They get aggregated at hourly scales and then uploaded automatically to various online databases. Right? So you can take a look at what's coming in as it arrives, more or less. To give you a sense of how many there are across Canada, this is where our Environment Canada stations are located. You see those black dots, those are our automatic weather stations. We've also got a couple of additional volunteer climate stations that are added at other places and run by ECC partner organizations. Then you've got things like the partner stations that are set up at aviation sites. And then in yellow, you've got a bunch of other things that are also feeding into Environment Canada's verification systems and might be used by Environment Canada for various different purposes. But those are, again, from partners, oftentimes things like industry or provincial governments that are running additional networks to add extra information. I just want to stress that when we take a look at this plot, what we've got here in colors are what we call a needs index, an indication of where we need weather information, usually reflective of different activities, but really, crucially, a reflection of where you would expect to see more weather hazards. So if I start taking a look at where the needs are high in reds and oranges, et cetera, we're typically talking about places that get severe thunderstorms, that might see the odd tornado, or that get things like large lake effect snowstorms that can suddenly show up and dump a lot of precipitation all at once. It's a bit of an indication of where we see frequent, very severe weather that requires observation and forward planning. That doesn't really perfectly reflect where we've put our stations. Instead, we tend to drop weather stations at places close to where people are living. So the higher the population density, the more stations you'll typically have around you. And that's just a reflection of the fact that these things are expensive to run and maintain, and they need somebody available to take care of them every now and again. Highly technical instruments, all of them are prone to failure here and there. You have to be able to maintain them. You have to have people around them. So we deploy them more on the basis of convenience a lot of the time than needs. Just to stress, though, that if we could get more stations out there, we would like to. We always want to keep these things out there and going. The more observations we can get, the better. Sounds like you've already had some discussion around CocoRa's, the Community Collaborative Rain, Hail, and Snow Network. This thing's an example of trying to fill that gap with information collected perhaps with a little bit less precision and standardization, but at much greater volumes, right? So the idea here is that if I give a lot of weather observers simple tools to collect information about precipitation, they'll be able to give me a more refined sense of what's actually happening. They will be able to account for some of the big differences across space that might be produced just by some anomalies in the precipitation that's passing, the weather system itself, local topography, all kinds of different factors that can change how we receive precipitation in one location versus how we receive it in a location even just a kilometer away. So the idea here is that many simple, if imperfect, measurements can complement those fewer, very technically standardized measurements from things like those automated weather stations. And again, anytime you want to take a look at what's coming out of CocoRa's observations, you can click on their website. You can take a look at a map that shows where the latest observations were collected. This is an incredible success story when it comes to what I would refer to as citizen climatology, right? People feeding into those climatological records. Now, I'm not sure what you guys are operating. It sounds like some of you are maybe doing CocoRa's related observations, but others have some weather stations. And I suspect probably this project is helping to deploy some of those weather stations. I'm not sure if you've got a standardized setup, if you've got one particular weather station type that you're trying to use. But regardless of what you have, there's a few things you want to think about when you're putting it out into the field. Again, when we're talking about citizen science, the observations don't necessarily have to be perfect, and you almost certainly don't have ideal sighting conditions around your house, but that doesn't mean that there's not value in here. The value can be amplified if we follow a couple of simple rules to the best of our ability. And that's to make sure that our weather station is sitting in constant sun. You don't want to have shade that passes over if you can avoid it. Constant sun. You want it to be sitting on top of grass or, failing that, a soil surface. Keep it away from paved surfaces as much as possible. You want to keep it away from shelter so you don't impede that wind flow. So you can make sure you're getting accurate wind direction and wind speed measurements. So away from trees, away from buildings, etc. And try to keep it on flat ground, just so you're not getting any influence from topography. Of course, depending on your setup, you're going to have to think about things like pointing that solar panel towards the south to make sure that it gets constant sun, and to make sure that you've got your wind direction calibrated properly so that when the machine thinks it's seeing north, it's actually seeing north. So a couple of just deployment setup conditions or considerations, but I want to stress that once you have it out in a location, try not to move it. The longer you're recording under the same conditions, the same site, the more useful that information is going to become in the long term. Now, I understand that people here are enthusiasts when it comes to weather. I was trying to think about what I would do with a weather station if it was in my backyard. And the first thing I thought about was trying to connect it to the kinds of weather forecasts that I've been looking at since I was a child, watching them on TV or reading them in the local newspaper. And those were typically tied to images like this one. This is from the States because I could still find something quickly available for today that represented some of those types of weather maps. And maybe ask for a show of hands if anybody has their camera on if you're familiar with these kinds of images. Leon's seen them before, maybe a couple of others. Perfect. So I would say that if I'm watching weather in my backyard, I'm also always taking a look at what these weather maps are telling me. What kind of things are passing by in terms of what we call weather systems. And in our latitudes and in our part of the world, the thing that I'm always looking for are those low pressure systems, right? Those low pressure systems that pass by tend to be associated with cloudy weather, and if they get particularly strong, those high winds that can create a lot of damage for us. And of course, also the fronts that are associated with those. So on an image like this, we see those lows marked. Some of them are stronger and more apparent than others. But on top of those, then we have these colored lines that represent what we call fronts. That's a boundary between air with temperature conditions of one type on one side, bumping into another patch of air, another air mass with different temperature conditions. If I've got a blue line like this, what that means is it's a cold front. It is cold air pushing into warmer air. If it's a red line like this, that's warm air pushing into colder air. Either way, I'm going to end up forcing the warm air above the cold air. That's going to produce some of my precipitation. Just to give you sort of an idealized example of one of these low pressure systems and its connection to fronts, here's an example of a storm that gets studied a lot. It passed through the middle of the United States back in 1997 and 1998. I've got 3 images here. Each of them are 12 hours apart, so we can see how this low pressure feature developed, moved across the United States, and carried those fronts with it as it did so. So if we start off, this system is relatively young at this point. I see it showing up and marked as an L for a low pressure system. It's surrounded, well, it shows up on the map here in black lines. These are isobars, lines of equal pressure. This is for pressure reduced to sea level, so we can see what conditions we're expecting to see at the surface. And those isobars, I can think about them as like topography lines on a topographic map. In this case, the lower values mean that we've got a valley, a low pressure through here. The idea here is, though, that this topography is going to move. In this case, if I move forward 12 hours, we see that the center of the low has moved towards the north and the east. I'll stress that the lowest pressure in here has dropped quite a bit. In the previous time step, the lowest pressure was about 996. Now it's dropped down to 992 and below. Those concentric circles are getting more tightly packed. When I see those isobars more tightly packed, I know that the wind speeds that are being driven by that pressure are considerably stronger. We see that the cold front in blue has tracked inwards into the United States, and it's started to catch up to that red line, the warm front. If I move forward another 12 hours, the cold front has entirely overtaken that warm front for within much of the system. The central pressure has dropped really low. This has now gone to 976 and below at the center of this thing. That's what we call explosive cyclogenesis, or what you sometimes hear referred to as a weather bomb or atmospheric bomb around us. All that means is we had higher pressures that suddenly just dropped dramatically. There's a criteria, I can't remember exactly what the threshold is, but it's something like 24 millibars in 24 hours. We've certainly got that here. This is a strong system. It created all kinds of damage, massive blizzard in the United States as it was passing through. But of course, those conditions vary depending on where you were. So again, if I'm watching weather, I'm always looking at weather maps like this. I'm trying to understand where the air is colder and moving, where the air is warmer and moving, where the pressure lines are getting more tightly packed, how the strength of this system is deepening, and how quickly, to get a sense of what I expect the weather to be. But if I'm also sitting there and taking a look at readings from a weather station, I might take a look at these particular diagrams. These are what we call meteograms. I believe if you take a look at your network's Weather Underground readings, you will get meteograms at the bottom of the page there, which allow you to then take a look at how different weather variables change over time. As a standard weather reporting graphic, in all of them, as we go to the left of the diagram, you go further back in time. As you move towards the right, you're going closer and closer to the present. And then you'll have a bunch of stacked graphs, each with different variables that are shown. Pressure is pretty common to see. Temperature and dew point give us a sense of, well, again, air temperature, how cold it is. The dew point then gives us a sense of how moist the air is or how much water it's holding. Wind speed's usually on there, often along with wind direction, represented in some way. In this case, it's with wind barbs. On this particular plot, I've drawn A and B to coincide with our diagram here, A and B. That's tied to this time period for A, this time period 12 hours later for B. What we can see is that if we're taking a look at readings from this red dot, which we are, this is Gage, Oklahoma, we're going from A, a point where the cold front has just passed over, to B, where the cold front is well away from us now. And on this meteogram, I can see that happening. I can see the pressure decreasing as my low pressure center deepens and passes over. But then as it passes away, the pressure again starts to rise. As the cold front approaches, I might not notice it. I'm just sitting in warm air as the thing's approaching. But as soon as it hits my location and then starts to pass, I'll see an abrupt drop in temperature. Whenever I see something like this, just a couple of hours, in this case, it's 2.5 to 3, we're seeing that temperature drop from about 25 degrees Celsius down to just about 10 degrees in just 3 hours. That's a strong cold front that's passed by. Usually these are associated with a change in winds. Ahead of the cold front, we'll see higher winds. Once it's passed, the winds will typically drop. And as it passes, the wind directions will often change direction just like that. Whenever we have a passage of a front, particularly one that's strong, we're very likely going to see some precipitation. And sure enough, that's what's listed here. These are just dots indicating moderate precipitation occurring just around when that front passes by. A warm front will show up somewhat similar. In this case, we've got this red location, which experiences the passage of a warm front from point A to point B. That's from time here to this time. Again, we see the passage of that front showing up as an abrupt change in temperature. Sometimes that'll come along with a change in humidity too. In this case, the low pressure system is not quite close to us. So we're seeing our position relative to that low pressure system shift. And that's here manifesting as a slow decrease in pressure. But you can see these wind speeds. Ahead of the warm front, winds are typically very gentle. But then after that warm front is passed, the winds will often pick up quite a bit. And again, a characteristic change in wind directions from along the front before the front passes, and then pushing behind the front once the thing actually passes over us. Took around in Camilo's backyard weather station data on Weather Underground to see what I could find in terms of the passage of a front from the recent past. And sure enough, I can see one here. Can anybody give me a sense of where they think that front passed and what kind of front it is, warm front or cold front? So show of hands. Who thinks it's a warm front passing by? Anybody think it's a cold front? Sure is a warm front. So it happens here between 9 a.m. 12 p.m., really between 9 and 10 is where we see this thing coming. We see increase in temperature that's relatively abrupt. It looks like it went from about 25 degrees to 35 degrees. And this will be Fahrenheit, I believe, sort of a default for a lot of representations of weather in the States. The same time that front passes, we see a distinct increase in winds. They were gentle before the warm front passed, but then went up after it had moved on. Our wind directions also change. Maybe the best way to describe this is they were very variable and low before the front passed, but then stabilized and stayed at the same level after it had moved on. And of course, here's a big spike in precipitation tied to the passage of that front. That warm air was being forced over cold air. As it was pushed upwards, you squeeze the moisture out, you make clouds, etc. I dug around looking for a surface analysis for this time from the National Oceanic and Atmospheric Administration in the US, which still provides some of these things in nice formats for us. If this is where my front was passing, this is a map that's relevant for that. And here I've just highlighted where Nova Scotia is, and sure enough, I can see that front right there. So these are the games that I would play with the weather station in my background. Can I see these weather systems moving through in the data that I've collected? How strong is that front as measured by the temperature difference that is produced when it passes by? What kinds of conditions did it bring with it? Those are the kinds of things you can do with it to start to read your weather data in the context of something bigger, your regional weather systems passing by. So again, what do I use these things for? Well, I mean, in your background, you can just watch these weather stations, you can have some fun, you can play around with this. But if I was somebody who was involved in disaster planning, disaster management, if I was thinking about taking care of transportation infrastructure, water resources, etc., I might be trying to get additional information about every significant weather event that passes by. The kinds of information that a network like yours can provide are information about variations in the weather event's manifestation across space. Get a sense of, for example, how conditions were different in Halifax versus Dartmouth versus Bedford versus Sackville. They all might see things a little bit differently, right? And so understanding how much rain has fallen in all these locations gives us a better sense of how the overall area around the Halifax metro area is being impacted by weather. That means that I can make sense of how topography is amplifying things, or exposure is amplifying things, or maybe mitigating some of the impacts a little bit. It helps me translate from just local interpretations to something much more regional. So if I'm watching precipitation at one weather gauge, I've got information that might tell me something about flood risk. But if I've got measurements from multiple weather stations, I can get a sense of how much water is falling, for example, over an entire watershed, all feeding into a waterway that might cause even greater flood concerns, right? Another thing that we think of here is that any weather station we deploy anywhere is going to complement our official networks run by Environment Canada. That means that we've got additional data that could be used to verify our forecasts, which allows us to improve our forecast systems and make better forecasts in the future. It also allows us to go back and take a look at where maybe some of our official observations have made mistakes, where maybe instruments have failed, or we're missing some data, or where we think there might have been some kind of bias in the system, because of course, every instrument at some point is going to have a failure. So if we have these additional measurements, we can sometimes step back and correct some of those bad readings at our larger stations. Of course, I'm a climatologist, so I like thinking about weather, I like thinking about extremes, but I always want to build it up into a bigger understanding of climatology. If weather is what we actually get from day to day, then climate is what we might expect to get, right? So I think about climatology as a succinct summary of likely weather conditions observed over the course of decades and informed by a bunch of different weather that's happened, again, over years and years and years. Ideally, something on the order of 30. Your weather stations are probably nowhere near that just yet. I know Leon's been collecting information for a long time, but many of you may have only had this for a couple of months to a year or two. The longer it's deployed, the more useful that information is going to become from a climatological perspective. What do I mean by a succinct summary? Well, we try to draw out the main features of our weather as it plays out in a given region and summarize it to make sense of what kinds of growing conditions we have, what kind of water resources we have available, and maybe even a sense of what kinds of risks we might face in that area. This is perhaps the most commonly used climate summary, graphical climate summary. So we call it climograph. This one is constructed from climate normals at the St. John's Airport over the period 1991 to 2020. It contains two key pieces of information. The bar graph here is showing us monthly total precipitation, averaged over this 30-year period. So for example, January in my part of the world, we are getting something on the order of 16 to 17 millimeters of precipitation on average every January. That drops to a minimum in June. That might be down to just 100 millimeters. So on average in January, it's about 150. On average in June, it's just a little bit more than 75. On top of that, we've got temperature lines. These are giving us daily averages, but not just the daily mean temperature, it's also the maximum average daily temperature and the minimum daily average temperature. So we get a sense of how temperatures are varying over the day. When we go from, if we don't have anything else happening, cold temperatures at dawn to maximum temperatures sometime in the late afternoon. This information gives me a sense of what kind of climate I experience, what kinds of conditions we bump into, a good sense of what I might be able to grow in this location. Temperature is a limiting factor for us, even if precipitation isn't. In Nova Scotia, you'll have considerably warmer temperatures in your growing season and a longer growing season that allows you to have a little bit more agricultural productivity and grow a wider range of agricultural goods. So this is all pretty useful, but I'd stress that it's still just scratching the surface of what a summary of weather conditions would look like. We can dig a little bit deeper, and if I go onto Environment Canada's website, I can find all kinds of other climate variables. So again, we've got some of our information here in terms of mean daily maximum temperatures, daily mean daily minimum. But then we've also got things like record low temperatures and record high temperatures that give me a sense of just how far away from those averages we get. Gets me into the extremes, right? But on top of that, we've got precipitation information that's further broken down into rainfall, snowfall, always useful in our part of the world. And then again, getting into some other climate indicators, like how many days of precipitation we have, and how many snowy days we have. All kinds of other variables could be examined. You could also dig into things like wind, which is a major concern for our part of the world as well, right? So this, again, is more than just that simple climograph. It tells us something about the extremes. It tells us something about the outliers. It tells us something about the range of things we might expect to experience while living for an extended period in a place like St. John's. If you want to start getting into the extremes in even greater detail, at any place where we're collecting regular weather information, people will be inclined to produce what we call an intensity duration frequency curve for precipitation. They might do it as well for wind speeds. This is how we start looking at extreme precipitation events, really extreme events. So hands up if you've heard people refer to things like the 100-year storm. Yeah, it's a common term, right? We're hearing more and more about the 100-year storm as the 100-year storm seems to be happening more and more often. It's showing up all the time. It raises questions about whether it's the 100-year storm anymore, right? So these intensity duration frequency curves are pretty technical, but the idea here is you say, well, okay, if I'm thinking about, say, for example, a 24-hour period, I might say, well, okay, what would I expect a big outlier storm to be? I might pick the 100-year storm. All that is a reflection of the probability. The 100-year storm has a 1 in 100 chance of occurring or being exceeded every year. So it's really just a probabilistic consideration, right? How likely is it to happen? Well, there's a 1 in 100 chance of seeing it this year. There's a 1 in 100 chance of seeing it next year. So I pick that probability and the amount of time that I'm considering accumulating that precipitation. I follow up from this graph to pick out, say, the 100-year storm here. And then I just track the graph along, and it'll tell me the intensity in millimeters per hour that that storm would have. If I multiply 7 by my 24 hours, I will get a sense of what my 100-year precipitation event is, right? Most of you aren't going to need to do this. Somebody else will tell you what the 100-year event is. But having additional observations helps us, it gives additional context to trying to figure out what these storms are, right? I just want to stress that those return periods, those 100-year events, that's just indicating likelihood. The bigger the return period gets, the less likely that storm was to occur. So when it shows up, you get a sense of how big a deal it is. The 2-year storm, I expect to see one of those every 2 years or so. There's a 50% chance of seeing that every year. The 5-year storm, there's a 1 in 5 chance or a 20% chance of seeing it every year, et cetera, et cetera. If you're collecting that information for a long time, you can start to improve your estimates of those 100-year events. And of course, the more information we have about observed events, the better we can try to understand what the future, what climate change will mean for these changes in extremes. That's what this plot tries to do. This was for St. Lawrence in Newfoundland and Labrador. This was produced by the provincial government here using some data that a colleague and I generated for them a couple of years ago. But the idea here is that in black, that's our current intensity, duration, frequency curve. So my 100-year event for the 24-hour period here, I track this number up, I hit my black line, and then I just trace it back to the intensity. And we see that it shows up at about 130, 135 millimeters per hour in 24 hours. That's my 100-year, 24-hour duration storm. Does that make sense? What happens if I go to future climate projections for the middle of this century based on some modest climate change projections? Well, that shifts everything to the green curve. Now, if I take a look then at what the same intensity is for 24 hours on the green curve that attaches right here at this point, if I track that down to my return period, well, now it's just the 25-year return period. My 100-year storm is now my 25-year storm. If I take a look at extreme climate predictions, the higher end of what models think might happen by the middle of the century, that 100-year event today becomes just the 10-year event in the future. That means that an event that every year had a 1 in 100 chance of occurring now, by the time we get to 2050, might have a 1 in 10 chance of occurring. It's gone up by a factor of 10. Which means if I've designed something to withstand that storm and expected it to last for roughly on the order of 50, 60, 70 years, I should probably take that lifespan and divide it by 10. Stuff will fail much more quickly. The risk has become much, much higher, right? These intensity duration curves require a lot of information. The more data that we have collected from additional complementary weather stations, the better. It'll help us nail down those numbers a little bit more concretely and reduce some of the uncertainty around these things. So I should stress that the more data that we collect, the better. That's always true. It sounds like the ESCOM network is relatively young, but its value as a weather and climate tool will grow as you deploy more stations and collect data at those stations for a longer period of time. Just want to stress that you want to interpret this data with care. Don't make the mistake of believing that just because you've got data that it's impartial, that it's authoritative, and that you know exactly what's going on. That can lead to some funny interpretations of what's happening. I'll give you an example, again, from Newfoundland and Labrador, where I talk about the weather all day, every day. Ever since I arrived in this province back in 2008, I have had people telling me, oh, you know, it's getting windier than it used to be. And I hear that every now and again when I first arrived. But the kinds of quotes and the number of times I would hear people mentioning the wind just got more and more frequent over time. And the nature of those wind discussions have shifted, right? So people will tell you, well, it's never been this windy. I've never seen winds like this. But then they'll start pointing to things and saying, hey, this building's been here for ages. and it got blown away recently. My buddy lost his shed. My friend lost their roof. They start characterizing it in different ways. Well, we used to have winds, yeah, but now it's dry when the winds are coming by, and it always used to only be windy when the rain was coming. So I take a look at all this information and I say, well, okay, something's happening to the wind gusts. And I wasn't the only person hearing this. The provincial government got in touch with me back in 2018 and said, hey, we've heard a lot about this and we tried to make sense of it. So we took a look at data from a bunch of weather stations over a long period of time in this province. They produced this particular illustration. What they're mapping here is for different weather stations, and you'll see that as more weather stations come on, they show up as new dots. But they're showing the annual maximum wind gusts. So the highest winds recorded at these stations every year as you move forward in time. We're counting down the years so you can see what we're recording. You see the stations listed as new ones come online. And they were taking a look at this and saying, okay, well, is it getting windier? And their overall interpretation might be a little different than those narratives we heard before, right? Hearing from a bunch of people that it's getting windier, the provincial government's looking at all the station data and saying, well, we think it's getting less windy. There's a bunch of concerns with this. One, I'll stress that this is a pretty limited interpretation of winds, just the biggest wind that you saw over the course of the year. That's not how most of us remember windiness. I don't think, well, the highest gust last year was 135. What was the highest gust this year? Oh, it's 132. It must be getting less windy, right? The other concern here is that we've sort of pushed together and aggregated a bunch of different measurements from a bunch of different stations, and it's hard to see a trend in any particular one. And it's not clear how much adding stations is just making for messier data interpretation here. But certainly this trend seemed to me a bit of a concern because it directly clashed what we're hearing from people. So a colleague and I spent a lot of time digging into this and taking a look at wind in every conceivable way, even while we were hearing from meteorologists that they don't see a wind trend. And ultimately what we found is something that makes some sense when you think about how people experience winds. If I calculate the number of days in which we had max gusts above a certain criteria, those associated with things like wind warnings or marine activity warnings, we saw that the number of days with max gusts greater than 25 knots, where you'd start to issue cautionary wind warnings, had actually decreased in St. John's, Gander. You can even see a bit of a decrease. It's not quite so clear in places like Goose Bay and Labrador, but it seems to be present across the province to some degree from the 1960s on up to about the mid-2000s. But then when we get into the mid-2000s and onwards, we start seeing that trend reverse. We started seeing more days where we'd issue wind warnings. That's actually a pretty sharp increase. So we weren't seeing unprecedented amounts of wind by this metric. Certainly it's something that we'd seen before in the past, back in the 1960s or 70s, but it is a real change relative to what people were experiencing in the recent past. There has been a shift. And so the thing that I just caution you to think about a little bit when you're checking your weather station is that you want to compare it to what your understanding of the weather is, what people's weather stories are, how they're interpreting what's going on here. People don't think in terms of annual maximum wind gusts. That's not something people experience and remember, but you remember when you've experienced a lot more wind days, when it seems like every day is windy, whereas just the odd occasional day is. So just a quick summary then, the ESCOM network, it continues a long tradition of citizen-oriented coastal meteorology. It addresses the original meteorological challenge, quantifying and preparing for marine and coastal weather risk. It complements other citizen science climatology efforts such as COCO-RAS. And it's really providing a chance to understand your connection, the connection of your particular location to broader regional weather. And it also gives you a chance to, again, connect your weather stories back to weather data to improve climatological interpretation. And with that, I'll dig through the questions that I've kind of seen jumping up, but I'll have to figure out how to find them here. There we go.
I can read them out.
Oh, sure. Go ahead.
Yeah. Let me pull up the questions. I guess to everyone, feel free to pop any questions in the chat as they come up. How do official weather stations measure snowfall?
So I think the last time I was taking a look at instrumentation for snow, they usually have a sensor pointed downwards that measures the distance to the surface. So as the snow collects, there's less of a distance there that these signals have to bounce off of to return. So that's one way to automate the snow depth measurement. But I'll tell you, I think in most cases, people are still going out there as well to collect hand measurements of snow whenever possible to make sure that we're calibrating things properly.
All right. What is the height above ground of anemometers in weather stations that to measure surface weather?
10 meters.
10 meters. Okay.
So it's usually I think it's 2 meters and 10 meters is what they usually try to set things up at. You're not going to have that in your backyard. Yeah.
Yeah. Yeah, I know that if from what I remember, both Cocoa Rush and Weather Underground has recommended, what is it? I think it is 5 feet to set up 5 feet above the ground, 6 feet above the ground, something like that.
Yeah. So that's roughly getting to the 2 meter nearer surface measurement. Yeah.
What's the ideal time period to analyze data over for each variable with a decent accuracy? What's the frequency to analyze data over for each variable with a decent accuracy?
Well, I mean, I would say generally speaking, hourly measurements are sufficient to see most things that would happen in your backyard. You don't need to get down to the point where you're looking at minute by minute data in most cases. Yeah, I mean, we have a small weather station that we operate here at an experimental plot up by the Botanical Gardens, just so we can see weather conditions as they occur. You can get higher resolution on those. You can go down to like the minute. But by that point, you're collecting all kinds of unnecessary data. If you go to an hour, that's more than sufficient to make sense of most weather events and most extremes that you'd want to touch on.
All right. And I guess building onto that, what if I wanted to like measure the average temperature for a week? Should I be looking at analyzing like temperature on an hour by hour basis and averaging that, or average temperature on a day and that?
Well, I suppose so. I mean, if you're averaging temperatures to get to the weekly average, it doesn't really matter too much whether you're taking the hourly data or the daily data. You're still going to end up with more or less the same average there, right?
Yeah.
There's been some efforts to try to understand how. Well, I'm trying to figure out how to frame this. There have been some people taking a look at whether old school averaging techniques, where you just took the daily minimum, the daily maximum, which you could record using old instruments. You would just average those two, add them together, divide them by 2. That would give you your daily average. Whether that compared to the average that you would get from an hourly estimate averaged over the course of the day. And the differences were apparent, but not dramatic. And that becomes important because we didn't used to have hourly recording instruments. You would instead have thermometers that you put outside. Every day you would go and check, and they would have a little marker in them that would record the lowest temperature that had been hit and the highest temperature that had been hit. You'd reset them, you put them back, you check them the next day. You keep getting those daily maximum and daily minimums, and that's really all the observations you had, right? So the idea is just using those the same as using the hourly observations. The answer was it's close enough that you can still use the you can still compare the current records to the old records. Does that make sense?
Yeah.
Yeah.
Thank you. How can we as citizen scientists make a climate graph with our weather data?
Okay, so the great thing is that if you're uploading to Weather Underground, you're already getting one. Otherwise, you can always sit down with some graph paper and just start plotting things out. Just write down those, you can take a thing of graph paper, you can put 24 hours on there. If you've got your hourly data, you can just plot pressure variables over time. You can plot temperature variables over time, et cetera, et cetera. So if you don't have a system that's going to upload those things and present it to you already, doing it by hand is probably the most educational way to start.
All right. So when you have 100-year storm, what's that like 1 in 100 data based off of? Is it based off of continuously calculated weather data, or is it based off of prior data?
It's based off of prior data. So most of those IDF curves, those are only updated occasionally because you end up wanting to collect high frequency precipitation information, like minute rather than hour. And so we don't deploy that equipment to do that regularly. So you set up occasionally some stations that for a chunk of time will be recording those higher resolution precipitation observations. And then you base your IDF frequencies, IDF calculations primarily on that data set. However, when you're talking about things like 24-hour precipitation, we have enough information to adjust those particular estimates as new events occur. So we can sit down and sort of ad hoc update some of those durations. But yeah, it's always based off of past observations. I'd make an argument that they're not updated frequently enough, given the impacts of climate change on extreme precipitation these days.
Mm-hmm. All right. And then what kind of simple analyses could we do as citizen scientists with our weather data?
Yeah, I mean, I would start by just taking a look at how the weather events manifest in your backyard. Next time you turn on the news, and I guess Ryan Snodden in Nova Scotia is telling you all about the next weather bomb that's coming through the province. Take a look after that event has passed by. See what your station has recorded. See what kinds of information you have. You can compare it between your different stations. You can see how that event differed from your various different spots, and just try to feel. To think about how that data reflects what you actually felt as that system was passing by, right? Mm-hmm. Yeah, I don't know. That's how I would start with this stuff. As you get more and more of the data, you can start thinking about, well, how does this match the kind, like if I start producing average monthly temperatures and total monthly precipitation, how does it compare to the climate normals that were recorded at the closest airport, for example, and see if you're showing a bit of a different climate than they were. But it's going to take a while before you can do a lot of those really interesting climatological analyses, right?
All right. So you mentioned it would take a while. About how many years would you say?
Well, I mean, before you're even scratching the surface of a climate, like by the time you get to 5 years, you can sort of start thinking a little bit about what an average looks like. But again, that's really just getting started. By the time you get to 20 years, you're getting a pretty good sense of what the current climate looks like. I know that's a long way in the future, but you'll be surprised by how quickly 20 years passed. Leon will tell you, he probably didn't expect that you'd be recording climatological information for 40 years back when he started. But 40 years can pass faster than you think as well, right?
All right. And then one last question. Could AI help us to analyze our data and be better prepared for extreme weather events?
So maybe, but with extreme caution. So one of the things that I will point to with AI is that really this isn't artificial intelligence at all. We don't actually have anything that I would refer to as proper artificial intelligence. We have increasingly complicated statistical probabilistic algorithms, right? The problem with extreme events is that they occur rarely enough that we have to approach statistics very cautiously. The problem with extreme events in climate change is that climate change can push us to extremes that were not possible in the semi-recent past, which means that we're moving into weather events that were statistically unimaginable even just 20 years ago. AI cannot anticipate things that it has never experienced very well. So if I start relying on AI as a means of understanding extreme weather and anticipating extreme weather, I really run the risk of being unprepared for those extreme events when they come through.
All right. Thanks for the explanation.
Yeah, no problem. Hopefully it was clear enough.
Yeah. Does anyone else have any other questions? Feel free to just open your mic and ask them or put them in the chat. All right. In that case, thank you for presenting this webinar to us, Dr. Joel Finnis. Before we close this out, I did want to also invite everyone, in addition to looking at their weather stations. Oh, Camilo, yes?
Just finish your idea. I just want also to give an invitation to everyone, but finish your idea, please.
I did want to give an invitation to everyone with their weather data, in addition to looking at current weather events and seeing if you can see them occur in your weather station itself. It might be really interesting to also see if you can make a piece of art out of it. A piece of art that represents something like a warm front or a cold front coming in, bringing with it a storm, or a piece of art representing the windiest day that you recently experienced and how the wind trends changed over the course of the day, or even how things change over the course of the year, things like humidity or temperature or wind. We're hoping perhaps to do an event where we get everyone's art pieces together and present them in an art festival in Eastern Nova Scotia. So I wanted to invite you all before the start of the new year to maybe think about making one of these art pieces. Camilo?
Yeah, I want to also to join your invitation, just to say that we would love to have all your support, but also to your involvement in this artistic weather initiative. Here, Abraham and I, we are here to support you. I know that Caroline Smith, she was leading this year this artistic weather initiative, but the idea is that all of you be involved. So it will be great that we start using the data. So this is just to follow your invitation, Abby. And the second thing that I want to add is that soon, I think in less than a month or 2 months, we're gonna have our own data management platform, and you can visualize the different the data from everywhere, and you can download your own data, and you can play, as much as you want with your data. So the idea is that it's nice that we are continue growing as a network with our weather stations. So now I think it's the time that we can start doing something with this data. Could be a scarf, it could be a blanket, but also could be a climograph. I really want to do once, as Joel showed us. I think we can do it our own small climograph for this year. We are just finishing the year, just to know which were the maximum, the minimum, the average of all of the 13, I think 11 or 13 variable that we are measuring with our weather station. And will be great, to show maybe in our freezer, that we have here. This is my the climograph for 2025 with my own weather station. I think it would be a great opportunity to have conversations with your community members.
For sure. Thank you for presenting, Dr. Joel Finnis, and I hope everyone has a lovely day.
I'll see you the 22nd of January will be our next webinar, just that pick the date, 22nd January, 6 p.m. And will be also that now we're going to be speaking about also weather stations. The idea was connect with this webinar. So we continue speaking about weather. So enjoy the weather until the 22nd of January. Merry Christmas. Have a great New Year.
Yep. Merry Christmas, folks. Have a great holiday season.